So we need to actually look at this multi-component diffusion equation. That means we need to look for something that is a substitute for Fick's law that was applicable only to a binary mixture. So we need to know what to do for a truly multi-component system. So let's now just write out this equation. It's going to go like gradient xi equal to sigma j equals 1 to n xi xj divided by dij vi vector minus vj vector plus yi minus xi divided by gradient p divided by p plus rho over p sigma j equals 1 to n yi yj times fi vector minus fj vector plus sigma j equals 1 to n xi xj divided by rho dij times dt comma j minus dt comma I divided by yj, I'm sorry, this ought to be like this, yj minus dt comma I divided by yi times gradient t divided by t. Should probably use a, okay. So does that look like Fick's law at all? Could Fick's law, so how, what does it mean? I don't understand. I just wanted to go from 2 species to 3 species. Would life get so difficult? Yeah, I guess when you get married you're going from 1% to 2% and life gets very difficult, right? So this is not terribly bad. Nah, here we can think a little bit more rationally than there, right? So if I were to basically say, can I reduce this to Fick's law situation? That means if I now say my capital N is equal to 2, would I get Fick's law back? Would I or would I not? Obviously not. This is obviously a monster when compared to what we were talking about previously. But if I now said I have only 2 species, would Fick's law be hidden in it? Could you see Fick peeping out of anywhere here remotely? Can you recognize him? Right. Yes, we can. First of all, how did we get this? Okay, I just pull it out of my hat and that's it? You just try to take it from me like it's like God given? The answer is pretty much like we said that Fick's law has to be from a molecular level basis instead of a continuum basis. We can derive this from a kinetic theory consideration, but this is actually considering a lot more than Fick did empirically deduce for his set of conditions. Okay, so we now are looking at about 4 different things, out of which Fick's law is contained only in this term first. Okay, because how can I tell that? Because I started out looking for a relationship between the mass diffusion velocity of species I to its concentration gradient. Okay, and if I were to look for a mass diffusion velocity related to concentration gradient, I really wanted to look for a concentration gradient in terms of mass fraction rather than mole fraction, but this is what I have. Okay, so any hope of getting Fick's law is from here, because that's what is first of all containing the mass diffusion velocity of species I. Unfortunately, it's also containing the mass diffusion velocity of species J, which is not equal to I. Okay, if it were equal to I, then you would have a 0 here, Vi minus Vi. Okay, so if you had two species, this is actually a convoluted expression for the gradient of mole fraction of one of the species in terms of concentration, mass fraction, mass diffusion velocities of the two species that are involved. So if I can now write this for gradient xa, okay, and then gradient xb, what I am actually looking for is an expression for Va and an expression for Vb. So now I have two equations. I can now solve for one of them, and then the problem is I will now have gradient xa and gradient xb, which I didn't have before, but then try to convert that from xa to ya and so on. Okay, so you start doing that, then you can try to get that. So whatever we were looking for is only in one corner of what the full picture is. Okay, so what's going on? So the first term denotes momentum losses due to collision with other species. This is the mechanism that is actually in play in Fick's law as well. Okay, and the second term, so we now start looking at what are these different terms. These are pressure related momentum changes. Pressure related momentum changes. The third term, we now have to explain what is small f. Small f is body force per unit mass of species I, is Fi vector. Fj vector is body force per unit mass of species J, right. So what is body force per unit mass? It's kind of like acceleration. Okay, so in a gravitational field this would simply be like g, except you would be wondering why would g be different for species I than species J. The answer is no, gravitational field mostly you're not going to be looking at here. This is more like things like electric fields, magnetic fields and so on. Okay, so where dependent upon whether your species that you are looking at is neutral or positively charged or negatively charged, you are going to have different body forces on different species, right. Therefore this term is primarily coming from a differential body forces. Okay, keep that in mind. I am highlighting this because as we are looking at the second term, there is a pressure related momentum changes. Go back and look at that. You had a gradient P over P that basically says that this is driven by a pressure gradient. That means a pressure gradient causes a concentration gradient is what you are essentially saying, but also keep in mind there is a coefficient yi minus xi. Okay, we will be looking for situations where these are not important. So for example here, if pressure gradient is not there, then there is no contribution of that to concentration gradient. Okay, or you could be looking for a situation when yi is equal to xi. When would that be? We talked about it, right. That is when all the species are having the same molecular weights. Okay, of course is a somewhat like a fictitious situation, but for ease of analysis we could assume that if you want to consider pressure gradient otherwise, okay, but you don't want, so we should be looking for when these different terms are important and so on. So one of the things here is you could get rid of this term if you don't have any body force to consider on any species in the first place, that means Fi and Fj all are 0, or if you have to keep body forces for some other consideration, get rid of here, you now take advantage of the fact that this is actually differential body forces. Therefore if the same body force is acting on this on all species, then don't worry about it. Like gravity, you want to take gravity into account, okay, but gravity is going to act on all of them, okay, then equally, then you don't have to worry about this term. So this is what's going to happen. So this is a differential body force term. Differential body force term, and so here for example Fi vector is body force per unit mass of species I. Same holds for J, and we are looking at the difference between the two. This is a vector difference, keep that in mind, okay. This is a vector equation on the whole, so this actually has 3 components in 3 dimensions, yeah, and so it actually caters to your need. We are looking for a Vi vector to be modeled in terms of concentration gradient, that it does that. This is a vector equation right away. And finally the fourth term, is called Sarat effect. This refers to thermal diffusion, okay. So Sarat effect thermal diffusion, that is diffusion caused by thermal gradients. Okay. When we are looking at the energy balance, we will look at the opposite possibility, that is, if you now have species of different concentrations, that could give rise to a heat flux, alright, that we will call that as a Diffusion effect, and this is a Sarat effect. These are named after these scientists. So here this is again, all these things are deduced from molecular level considerations like in kinetic theory, and what you would find is that if you had temperature gradients, as you can see here, so if you had a temperature gradient that contributes to a concentration gradient, okay, so that's the effect that we are looking at, okay. And we won't derive this as I said, we just state this, okay. Now it can be shown that means you show, okay, shown that for a two component mixture, we can write y1 v1 vector is equal to d12 gradient y1 minus y1 y2 divided by x1 x2 times y1 minus x1 times gradient p over p minus y1 y2 divided by x1 x2 the whole squared rho over p f1 vector minus f2 vector plus dt comma 1 divided by rho d12 gradient t over t. Now dt comma 1 or dt comma I in general refers to what's called the thermal diffusion coefficient. Okay, so dt comma I refers to a thermal diffusion coefficient that just shows up here or here. Okay, now typically you can always see that okay, let's just look at the units of this equation here. You're looking at gradient of x. Okay, x doesn't have any units, it's a mass, it's a mole fraction. Okay, so gradient will have like 1 over meter kind of thing, so you're looking at 1 over length kind of units. Gradient t over t also has same units. Okay, because the t units get cancelled and then you have only gradient of something non-dimensional. Therefore and of course you look at this x and y, they don't have any units. Okay, so what matters for you is d over rho dti or dtj divided by rho dij is what should be dimensionless. Okay, I'm sorry, yeah, that's right. So this is having the same units as this, that means everything else should be dimensionless, and since x and y don't have any dimensions, dti over rho dj, that's how typically we would compare things. So dti divided by rho dij is small. Alright, typically. So now just to get an idea of what's going on, if you were to just look at the dij alone, it's the highest for gases. Okay, that means gases can diffuse very fast, alright, but lower for liquids and then still lower for solids. You could be thinking about solids also going through molecular level diffusion, alright, like in alloys and so on, but that's a very slow process when compared to what happens in gases. So this is fairly high. So if you compare these, they're like orders of magnitude different, as you will see. But if you now compare the thermal diffusion coefficient with the rho of the mixture times dij for a pair of gases, then this is obviously not for a pair of gases, this is for one particular gas, alright, whereas the dij is a binary diffusion coefficient, it's for a pair of gases. Okay, the other thing that I would like to point out is when you now have a multi-component diffusion equation and you're looking at the same process that was there in Fick's law showing up in this term, you're still retaining the binary diffusion coefficient and then summing over all other species than what you're talking about. Okay, we didn't have to explicitly say that j is unequal to I over here because that would contribute to a 0. Okay, so you could just sum over, but essentially we are looking at the interaction of all other species one at a time with species I. Okay, so it's as if you now have a multi-component mixture and you're looking at what is the concentration gradient contribution due to mixing for a particular species. It's coming from this species interacting with all other species individually, in mixing with all other species individually as pairs of this species and each of those other species individually. Okay, and as I said, dij is equal to dji for any pair I and j, and so it is like as species I is mixing with any of the species j, other species j, all other species j are equally mixing with species I in turn. Okay, so it is kind of like if you now have a group of people and then you now let a bad guy in, this bad guy actually interacts with each of the guys in this group. So every person in this group is equally responsible for entertaining this guy and contaminating the group, you see. So this is what's going on. We are now still looking at a binary interaction and a collective effect of the binary interaction over here. Alright, this is a little bit indirect, because we would like to think of a diffusion coefficient that is a function of only one species at a time. We don't want this pairs of species business, because when you think about a thermal conductivity or a specific heat or something of that sort, we can easily think of those as being properties of only one particular species, right? But it's diffusion coefficient, we have to think about a pair of species at a time. That makes things complicated. We will try to work around it by some kind of assumptions and simplifications a little later, but at the moment I have to point out that's how the process is. Mixing always involves minimum of 2 species at a time, and we always can look at them as a process that involves 2 species at a time, even in a bunch of species together, right. So that's the reason why the same binary diffusion coefficient that we saw for a Fick's law shows up here, and that's exactly what it is here as well. Okay. Now we can, as I was talking about, we were trying to get rid of some of these terms so that we can now begin to see the Fick's law come up, right. And I also told you, can we apply this, can we apply this to a binary mixture, and that's this result. You can see that this is a little bit different from that. That means some simplification has been made. Okay, it's been made so that we actually have y1 v1 vector, which is the diffusion mass flux. That's what Fick's law was looking for, okay, to get you something in terms of concentration gradient, in terms of mass fraction gradient, right. So this is already rewritten in this form that we want. Now we have to look for what are the conditions under which you can make simplifications and retrieve Fick's law out of here. So under certain assumptions, and that's what we have to see now, certain assumptions. Under certain assumptions, the Fick's law is recovered. Okay, that is to say, we can say y1 v1 vector is equal to minus d12 gradient y1. Did we see this? Well, all you have to do is put in a row on either side. If you now put in a row y1 becomes rho1 v1 vector becomes j1 vector, and that's equal to minus rho d12 gradient y1. That's exactly what we had before. Okay, so this is pretty much the same as what we saw for the Fick's law. So the assumptions are, one, the mixture is binary. Of course, we are looking at applying this to a binary mixture in the first place. The thermal diffusion is negligible. That's the Sarat effect, that is in whatever we do in our class, we will always be pretty much assuming that the Sarat effect is negligible, because dTi divided by rho dij is much less than 1. We won't worry about it for most of the conditions. Okay. 3, body forces are same on both species or negligible. You have two choices of making assumptions. Okay, so you can assume that the body force is the same even if they are not negligible, or if you have to get rid of it, you have to make an assumption that it is negligible. The question basically is, for example, if you are now looking at buoyancy effects, that means you can't get rid of body force. Okay, buoyancy effects in flames, and that's very typical under gravitational conditions. Look, the reason why you see these candle flames looking elongated upwards is because we are in Earth's gravity. If you now go to a zero gravity environment, you won't see this kind of a shape, right? So if you want to actually think about that effect, not exactly that effect, I mean there are some things that go associated with that shape for as far as the heat transfer back and all those things is concerned. So from a quantitative point of view, gravity does affect not just the shape of the flame but lots of other interesting parameters. So you might want to keep gravity, but fortunately for us the gravity would affect different species to the same extent, so that's fine. So it doesn't affect this equation, it shows up in the mixture momentum equation. Okay, so keep it there, you don't have to worry about it here. Constant pressure or constant or uniform pressure, constant or uniform pressure, or identical molecular weights. Right, either of them will sell. If you had a grad P that is 0, that's okay approximately, or if yi is approximately equal to xi, that means both the molecular weights approximately the same, then that would work as well. Now how good is this assumption, or either any of these assumptions? The answer is not terribly bad, although it's not strictly valid in most conditions. You can think about, so many times when you're looking at assumptions, you have to ask yourself, is it a reasonable assumption to make, or is it completely unreasonable just to make our lives simpler? Alright, the answer is you will find, we will go through this quite carefully. We will note that under typically low Mach number conditions, alright, and most combustion processes that we commonly encounter, right from candle flames, Bunsen burner onwards, kitchen gas stoves onwards, to even highly turbulent flames in furnaces, gas turbine combustors and power plants and all those things are all fairly low. Rockets, okay, are all fairly low Mach number. How low? Any ideas? How low is low? 0.2, 0.3 is low. It's not even that high. Okay, typically it's 0.1 or less. Many times it's like 0.01. Alright. Now if you really think about what I am talking about, okay, now at these kinds of temperatures that we are looking at, the speed of sound is so high. So you are looking at something like close to temperatures close to the adiabatic flame temperature, the speed of sound is like of the order of 1000 meters per second, right, and 0.1 times that is going to be like 100 meters per second. That's going to be very fast. It's not slow really, strictly speaking, but the Mach number is low because of high temperatures involved, you see, and typically we are looking at fairly low subsonic conditions for most of these, and what we will show is under those conditions it is okay. We will show that the pressure actually becomes constant more or less. Alright, so this is not terrible. Or if you now look at molecular weights, if you think about molecular weights between, for example, nitrogen and oxygen, there isn't hardly any difference. Okay, so like you're looking at between 28 and 32. Carbon monoxide is what, about right, 16 plus 12 is again 28. Okay. Carbon dioxide is a little bit of a high on the higher side. but methane could be like about 14, water is like 18, so they are all in the same ballpark for most parts. So it's not a terrible assumption under most conditions. You shouldn't worry too much about the molecular weights being too disparate. They are not for most conditions. So for analysis purposes it may be okay to make this assumption, but not a lot of times. For example, you're looking at propulsion, you have like the specific impulse or something like that is going as like square root of T divided by molecular weight, and it's in the denominator. So if you now have a small change in the molecular weight, like let's say from if it changes from let's say 30 to 20 or like 28 to 18, it makes a difference. It makes a significant difference in your ISP calculations and so on, and people die for getting that kind of increase in ISPs from there. So you got to be careful on the application, and you might be able to get away with assuming equal molecular weights for the purpose of getting rid of this term, or for the binary mixture this term. So then with these we can get the multi-component diffusion equation to reduce to gradient xi equal to sigma j equals 1 to n xi xj divided by dij times vj vector minus vi vector, right. That's what we can get it to. So if you want to now make sure that this is a binary mixture, make this I is 1, and so j equals 1 to 2. We can now make this x1 xj d1 and so on, and v1. What we are interested, if you now go back and look at this and this are there, okay. Don't have to worry too much about d1j, because j goes from 1 to 2 and j is unequal to 1, so this is just going to be only one term, right. So we don't have to worry about a summation. You can j is going to take only a value of 2, and therefore you can get rid of this and then start putting your j as 2 for you. You can now have a j2 d12 and v2. The problem that I am talking about is you now have v2 x2 and x1 as distractions from this expression. See, they don't and then of course you have x1 here. We wanted a gradient y1, but this is an expression for gradient x1, okay. So you know how to convert y's to x's, okay. There is a relationship between x and y for each species, which involves all other species, that unfortunately, okay. But this is a binary mixture, therefore it should be possible to for you to figure that out. And you also have to eliminate v2, that means you will have to consider the next equation and so on. Keep in mind, in a binary mixture x1 plus x2 is equal to 1 and y1 plus y2 is equal to 1. You should use those additional equations, and then you should now simplify this to something like this. That's an exercise as well for you to do, right. Okay, I think we'll stop here for the day. We started too late.